Before we look at example 11, let's look at the formula to work out what the normal distribution would be for an approximation to the binomial. So let's say we've got x, which follows a binomial with n trials, and p is the probability of success. Then we can approximate this to a random variable y, using a random variable y, which is normally distributed. Now, the mean of the normal distribution is NP, and the variance is NP 1 minus P. We don't need to worry too much about where this NP 1 minus P comes from, but the mean of the normal distribution kind of makes sense, because we want the mean of the normal distribution to be the same as the mean of this binomial variable. And well, if you're doing n trials and the probability of success is p, then we would expect x to be, on average, n times p. If you look back at the example that we did here, we had 20 trials, the probability of success was 0.5, so the average of x is going to be 10. The mean of x is 10, which is where we get np from. You might also see this written as mu is np, and sigma is the square root of np 1 minus p. So here they've just given you the formula for the standard deviation, whereas here I've written the variance, because remember this number in our bracket is the variance, which is np 1 minus p. They've just square rooted it. And we need to remember the conditions for what makes this a good approximation. So this is only a good approximation if the following conditions are satisfied. N has to be large, and P, the probability of success, has to be close to a half. And we're not actually told how large n has to be or how close p has to be to 0.5. But in the exam questions, it'll always be fairly obvious whether n is large and p is close to 0.5. And you'll be able to tell from the context of the question the kind of answer that you need. So let's have a look at example 11. So we're flipping a coin 100 times and we're told that the coin is slightly biased towards heads. So the probability of getting a heads is 0.53. So our random variable x counts the number of heads that we get when we do the trial 100 times. So x is going to be binomially distributed, n is 100, and p is 0.53, the probability of a success, which is getting a heads in this case. So that's our value of n, and this is our value of p. In part B, we're asked to explain why x can be approximated using a normal distribution. Well, here we just need to use these two conditions here. We've got a large number of trials, so n is large, and we should relate it back to the question into the context. So we could say that, i.e. this is because we're flipping the coin a large number of times. And our second condition is, so we should probably say and, also p, the probability of success, is close to 0.53. Close to 0.5, sorry. 0.53 is close to 0.5. Okay, and in part C, we're asked to find the values of mu and sigma for this normal distribution. So remember, our approximation approximately is going to be y follows a normal distribution. Now mu is going to be np, and the variance sigma squared is going to be np 1 minus p. So let's write down what that is in this case. So that's y is going to be a normal. np is going to be 0.53 times by 100, which is 53. And the variance is going to be, so np was 100 times 0.53, which is 53. And that's mu. And sigma squared, our variance, is NP 1 minus P. So that's going to be 100 times by 0.53, and 1 minus P is 0.47. So if we work that out, we get the variance is 24.91. So 24.91. So that's our normal distribution here. Now we should probably say what the value of sigma is. Remember, this is the variance. We were asked for what is sigma. So sigma is the square root of the variance, so the square root of 24.91, which we can work out as 4.99 to 3 sig fig.